I'm Andrew, and I'll be presenting Benchtop 19F NMR Spectroscopy Optimized Knorr pyrazole synthesis of Celecoxib and Mavacoxib, which are three trifluoromethyl pyrazole benzenesulfonamides, non-steroidal anti-inflammatory drugs, also known as NSAIDs. In this presentation, I'll go over fluorinated motifs, specifically fluorinated pyrazoles, and their role in medicinal chemistry, specifically Celecoxib and Mavacoxib, which are selective COX-2 inhibitors, and talk about how our investigation and results on how KQ can affect the synthesis and reaction kinetics and mechanism of the synthesis of Celecoxib and Mavacoxib. So fluorinated motifs in pharmaceuticals have, over the past 20 years, been increasing in prevalence due to the improved metabolic stability and improved bioavailability and potency. And in fact, over the past 20 years or so, have accounted for over 20% of FDA-approved drugs. And specifically, fluorinated pyrazoles have been reported in over 60,000 patents and manuscripts and used in a variety of therapeutics and agrochemicals, and have been associated to be responsible for the anti-cancer and anti-inflammatory properties of many pharmaceutical drugs. Some of these drugs are listed here on the right. Our compounds of interest, Celecoxib and Mavacoxib, are COX-2 selective inhibitors, which mediate the conversion of arachidonic acid to inflammatory prostaglandins. Celecoxib, which was FDA approved in 2004, and Mavacoxib was approved for veterinary use in the EU, both to treat inflammation and swelling in a variety of patients. Both are synthesized through the cyclocondensation of a 1,3-dicarbonyl and a hydrazine, and we screen this reaction through a variety of protic and aprotic solvents and Lewis and Bronsted acid catalyst. This reaction, called the Knorr-pyrazole cyclocondensation, works through the condensation of the hydrazine to the 1,3-dicarbonyl, which undergoes a 5-exotrig cyclization followed by dehydration to afford the final product, Celecoxib or Mavacoxib. Previous work in our lab has demonstrated the usefulness of 19F benchtop NMR, specifically the quantitative and mechanistic analysis of the Biginelli cyclocondensation of monastrol, which was published in ACS Omega. And therefore, with a similar workflow, we decided to investigate how KQ can affect the reaction kinetics and mechanism of the Knorr-pyrazole cyclocondensation. This is possible because 19F NMR actually reveals many transitory intermediates, such as the product and many other, and the keto and enol tautomer of the 1,3-dicarbonyl. And if you look at the NMR time lapse on the right, you can see as time progresses, the product peak, which is highlighted in green, increases, while the starting material, keto and enol tautomer, decrease. Previous experiments have actually resulted in irregular formation of the product with inconsistent data shown by the high error bars. However, once we actually started equilibrating the 1,3-dicarbonyl solution 30 minutes before we started adding the hydrazine solution, we actually found that it formed our expected first order curve for the formation of product and extremely small standard deviation values. And we performed these experiments in triplicates. And additionally, the KQI is defined as the keto tautomer divided by the enol tautomer of the 1,3-dicarbonyl, which are actually in equilibrium with each other. And so with over 3,600 NMR scans that are involved in experiments, we found that overall in Celecoxib and Mavacoxib, only the protic solvents stabilize the keto tautomer, while the aprotic solvents favor much less, specifically DMF and NP, which actually show no keto tautomer. And we hypothesize this is due to the aprotic solvent's polar OH bond, which is able to disrupt the intramolecular hydrogen bonding that stabilizes the enol tautomer. Additionally, with the initial rate, we found actually that DMF produces the fastest initial rate, even though we've seen that it actually doesn't stabilize the ketotomer, which is the reactive form of the 1,3-dicarbonyl. However, we hypothesize this is actually due to DMF's aprotic solvent's ability to stabilize the reaction intermediates due to the ability to act as a hydrogen bond acceptor. And this is consistent across Celecoxib and Mavacoxib. Once we compare this initial rate against the KQ in the aprotic solvents, we actually find there's a positive correlation such that more ketotoxin can be attributed to a faster formation of product. Additionally, when we the product after 4.5 hours, we see that methanol generates the highest. Methanol conditions are the highest yielding in both Celecoxib and Mavacoxib. And when we compare it against KQ, there's actually a positive correlation in all the solvents, and therefore, and this is also consistent in Celecoxib and Mavacoxib as well. Additionally, previous literature has demonstrated the formation of a stereoisomer in the same reaction. However, when we performed the reaction, we found that it only was formed in methanol, which we presume is due to methanol's ability to be a competing nucleophile, where it forms a dimethylketal with the 1,3-dicarbonyl, resulting in the hydrazine performing a nucleophilic attack on the carbon 1 position of the 1,3-dicarbonyl instead of the carbon 3, which results in this 5-trifluoromethyl regioisomer. And additionally, we've seen that there's actually not really much impact of the catalyst on the formation of this regioisomer, as is relatively inconsistent. And so, in conclusion, we found that for the initial rates, KQ can possibly be correlated in ethanol and methanol. However, there's a positive correlation between KQ and products across all solvents. Additionally, we found for the reaction rate that the reaction actually performed the fastest initially in DMF and slowest in ethanol. And the highest yielding conditions were found in methanol and least in DMSO, and that only methanol produced the regioisomer in both compounds. I'd like to thank my fellow project members and my advisor, Dr. Edward Njoo, and ASDRP for allowing us to conduct this research. Any questions?